Ladies and gentlemen, may I have your attention, please? Our next parallel session is about to begin. Please take your seats. Once again, our next parallel session is about to begin. Please take your seats. Thank you.
Welcome back. Our next speaker is Senrui Chen. He will talk about efficient self-consistent learning of gate set Pauli noise.
Thank you for the introduction. Hi, everyone. I'm Senrui Chen. Thank you for staying till near the end of QIP this year. I'm going to continue talking about something about Pauli channel. The title of my talk will be Efficient Self-Consistent Learning of Gate Set Pauli Noise. So let's jump right in. Over the past few years, we have seen many very exciting development in quantum information processing, especially in how we deal with noise. We now have below threshold surface code demonstration, and we have based on reconfigurable atom arrays, we can do some kind of logical computation. But noise remains as a major challenge in quantum information processing. So the topic of my talk today will be learning about noise. Why do we want to learn about noise? Well, there can be many motivations. For example, we just want to calibrate our device and do benchmarking of our device. And with the knowledge of noise, we can do error mitigation. And also, the knowledge of noise can help us improve the design for quantum error correction. For example, with the knowledge of bias noise, you can design better error correcting code. And also, maybe you can use the information to improve your decoder. I will focus on a specific noise model called Pauli noise model. But for now, let me first define Pauli channel. You probably have already seen that in the previous talk. So an n-qubit Pauli channel is basically defined as a probability mixture of n-qubit Pauli operator with a small pa denoting the Pauli error rates. It's a probability distribution. And any Pauli channel can also be alternatively written in the form of the right-hand side, parameterized by a set of parameter lambda b, known as Pauli fidelity or Pauli eigenvalue. This is because if you input a Pauli PB into the Pauli channel, you will just get that PB proportional to some lambda b, just like an eigenvalue. And we'll make an additional definition of symmetric Pauli channel. That is, when the Pauli fidelity of your Pauli channel only depends on the Pauli pattern, we call it a symmetric Pauli channel. Here, a Pauli pattern basically means the support of a Pauli. For example, the pattern of xi, is defined to be 1, 0, 1, 1, 0. So this kind of symmetric Pauli channel is also known as generalized depolarizing channel. Okay, with this, let's define what is a Pauli noise model. Suppose now we have an n-qubit system, and we have the following allowed operation set. We can initialize to the O0 state. We can apply layers of multi-qubit Clifford gates, and we can do layers of arbitrary single qubit gate that are not necessarily Clifford, and we can measure in the computational basis. This will give us a universal gate set for quantum computation. But now, in real experiment, we know that all of these components are actually noisy. But let us consider a very specific form of noise model here. I assume the state preparation and measurement and all the multi-qubit Clifford gate are subject to some Pauli noise channel denoted by lambda. And I assume the single qubit gate has negligible noise. Here, a little point is that I assume the lambda S, lambda M, the span Pauli noise channel, to be a symmetric Pauli channel. And I assume all the gate noise channel to be actually gate dependent. Means for different layer of gate, it can have different Pauli noise channel. Although this assumption might sound like a little bit of assumption, this can actually be ensured using a technique called randomized compiling, given that your system has pretty good and pretty fast single qubit control. What you do is basically you insert a lot of single qubit Pauli gate to twirl off the noise into a Pauli channel. And the reason we like Pauli noise model is it really have a lot of application. Here, just list some example. You can use that to do benchmarking. You can use that to do error mitigation. And you can use that to optimize decoder for your error correcting code. But let's consider another issue of Pauli noise model. So here, for what I defined just now, I call it a complete Pauli noise model, which means that, okay, the noise channel here are all parameterized by full parameter Pauli channel, which means it has 4 to the n minus 1 degree of freedom. An obvious issue is that there's exponentially many parameters there, and it is very difficult to learn them and to use them. So in practice, we usually consider something I call the reduced noise model. That is, we consider a polychannel with some efficient answers. So like, we maybe consider some fully local polychannel, and we might consider some quasi-local polychannel. I will come back to the definition later. But what is important here is that for this reduced noise model, the number of parameters are like a polynomial, and it's easier to learn and work with. Okay, great. So the main question of my talk today is the following. How do we self-consistently learn a polynoise model? Here, by self-consistency, I basically mean I just want to use all these noisy operations to learn about themselves. This is also, known as learn everything spam robustly. But here, I also want to learn the spam itself. So basically, I want to learn everything with noisy separation, noisy measurement, and noisy gates. Turns out this task cannot be fully solved in general. That is, lambda, all these polychannels cannot be fully determined self-consistently, as shown in these two earlier work. There are actually many attempts to solve this polychannel learning task. There are many protocols, cycle benchmarking, ACES, and randomized benchmarking type tomography. One thing I want to highlight is the principle of gate set tomography. It actually shows that in this kind of noise model, there always exists something called a gauge freedom. And I will actually give an example of gauge transformation to help you see that why the polynoise model can not always be fully determined. Consider that now we have some invertible linear map denoted by M, and we try to use this map M to acting on the polynoise model I just defined. I act M on all the initial state I prepare. I act M inverse before all the measurement I do, and I conjugate all the multi-qubit and single qubit gate by M inverse and M. And after this transformation, I get a new set of initial state, gate, and measurement. Here, actually, if you choose this map M appropriately, you can actually preserve all the assumptions of a polynoise model. As an example, if I choose the map M to be a depolarizing channel on a subset of qubit, for example, on the first two qubits, you actually see that the model will still be a polynoise model. Why is that? So if you look at the separation noise and the measurement noise, they're still polychannel pretty obviously. Because depolarizing channel itself is a polychannel. If you combine it with another polychannel, it is still a polychannel. And the depolarizing channel commute with single qubit gate. So actually, they will cancel each other. The single qubit gate will remain noiseless. And finally, the depolarizing channel commute with a two qubit cleaver gate. It will no longer be depolarizing channel, but it's still a polychannel. So everything here is still a polychannel. So if you group all the new lambda S prime, lambda G prime, and lambda M prime, you get a new polynoise model, just with possibly with different parameters. Here, let's just assume the transformation is small enough so that everything after transformation is still completely positive. We will call this kind of transformation a subsystem depolarizing gauge transformation. So what is the point of doing this gauge transformation? Well, this is because we can claim that if you have two sets of parameters of a polynoise model that is related by a gauge transformation, they are actually indistinguishable self-consistently. And this is easy to say. For example, you have on the upside, you have an original noise model, and at the bottom, you have another like gauge transform noise model. And if you just go back to the second row, you will see that all the gauge transformation map D and D inverse will just cancel each other. So that means that for any circuit you design with these two noise model, you will always get exactly the statistics, so that there's no way for you to distinguish these two models within this, using this operation set. And also, so if you consider now you have some function of the noise model, like the fidelity, the average fidelity of the gate set, the span fidelity, whatever. If your function is can actually be changed using certain gauge transformation, then we can conclude that your function is not self-consistently learnable because it takes different value at indistinguishable noise model. So our question here is that how can we characterize all the learnable functions of a model and all the gauges of a polynoise model? And here I want to highlight that this question becomes even harder if you consider a reduced noise model, that is a polynoise model with some additional answer. This is because in this case, some gauge transformation will become invalid because of the answer. Look at the same example I have, but now I consider fully local noise model. I still consider gauge transformation on the first 2 qubits. You will see that after the transformation, you will still get a polynoise model, but the poly channel is no longer a fully local poly channel. For example, for the second gate, you see that the noise become on 3 qubits. So if you really believe your system should have a fully local noise, this kind of gauge should be frozen. So the question we want to ask is, can we characterize all the learnable functions and gauges for a generic reduced polynoise model? I hope I have made the setup clear. Now I'm going to explain our solution to this problem. So our first step is we want to put the polynoise model, the parameter, in a linear space. Let's start with a complete model, such that all the polychannels are just n qubit. They are easier to work with. I will first define X to be a vector of parameters. What I do is I just consider all the polychannel for span and for all the gate, and for all the poly A. And I take all the lambda A, a minus log of them, and define them to be X, and I just write down all of them as a vector. And now I pretend this vector is live on some like real linear space. I will call that the parameter space. Basically, that's a linear space that your all possible parameters can be taken in. Let's forget about the positivity issue for now. It's just a linear space. And then I can define something called an experiment. The experiment is just a mapping from your noise parameter space to a n-dimensional probability distribution. And it's given by you just specify the gate sequence. And I will run the circuit and get a bunch of measurement outcome. And this outcome has the outcome distribution has a one-to-one correspondence with your noise parameter X. And arguably, this is the most general kinds of experiment you can do with this model. And because of that, we can then define something called the learnable function. I call the function about the noise parameter is learnable if and only if it can be determined by some set of experiments. Here, I will just consider linear function. But I have an argument that linear functions suffice, but I don't have time to explain now. So please bear me with that. And I can also define something called a gauge vector. That is a vector such that if you consider any noise parameter X, and you add this noise parameter X by some gauge D, it cannot be noticed by any experiment, right? So it sounds exactly like a gauge transformation. And the linear space spanned by the learnable functions and the gauge vector, I will call it learnable space and gauge space. So our question now is very clear. How do we characterize the learnable space and the gauge space? So the method we do that is to use some graph theory. We'll put all the parameter on the graph. So this part is actually like slightly modified from earlier work I have with Yunchao Liu and other collaborators. We'll define a graph called pattern transfer graph. So this graph will have 2 to the n-1 node denote a poly pattern, which is basically a non-zero NB string. And we have an additional node called the root node. Now we put all the noise parameter on the graph. We first consider all the state preparation fidelity parameter. Because it assumed to be a symmetric polychannel, the noise parameter is only depend on the pattern. So we'll have like a vector of edge from the root node to all the corresponding pattern. And label S means it's a state preparation noise. And for the measurement noise, it will go in from a corresponding pattern to the root node. Finally, for each gate and each poly, I will have an edge from pattern of poly A to the pattern of poly GA. For example, in this graph I consider the gate of CZ. And if you consider acting the gate CZ on, for example, IX, it will transform IX to ZX. So that means you transform a poly of pattern 01 to pattern 11. So we'll have an edge here and label it by E, IX. Okay, so now we define some like a linear space also on this graph. So first, all the edge on the space, we can think that they can formally span the real linear space. I call it edge space. And all the cycle on this graph will span the subspace called the cycle space. Here as an example, if I consider a cycle here, it can have like 3 edges, like E01S, EIXG, and E11M. I'll just add them together. So this is a cycle. And the cycle space is spanned by all cycles. Also, I can define something called a cut space that is spanned by all the cut vector. As an example, I draw a cut of this graph, and for all vector going from one side to the other side, I will have a plus, and for all the edge going from the other way, I will have a minus. This will define the cut vector. So a well-known lemma from algebraic graph theory will say that if you define this way, the cut space and the cycle space will actually be orthogonal complement of each other inside the edge space. Okay, so our main theorem actually kind of modified from the previous paper, saying that there's a nice characterization of the learnable and gauge space just using the linear space on the graph. So specifically, all the learnable function actually corresponding to cycle on this graph, and all the gauge actually corresponding to cuts on this graph. How do we prove that? Well, we actually just need to show two things. One thing is cycle are learnable. The second thing is cuts are gauge. Now I will sketch the proof for this. The first thing is the cycle is learnable. Let's first define something called a rooted cycle. That means the cycle passes the root node at least once. For example, the blue cycle is such an example. And we can show that any rooted cycle can actually be learned by certain experiment. More precisely, there will exist a certain Clifford gauge sequence and a Pauli measurement, such that the expectation value will exactly give the corresponding rooted cycle. And if you go to the talk about simulating noise circuit, you can kind of understand this as a Pauli path, as they say. So it is like you can always single out a certain Pauli path as long as it is the rooted cycle in this graph. So this means that all rooted cycle can be learned by certain experiment. Also, by construction of our graph, this kind of rooted cycle will span the whole cycle space, basically because our rooted node strongly connected to all other nodes. So this means all function in the cycle space Z is actually learnable. I don't have time to talk about how you actually design the learning algorithm, but there's a most naive learning algorithm that is immediate from the proof. That is, you can basically find the rooted cycle basis for all the cycle of the graph and just learn them one by one using the corresponding Clifford circuit of this cycle. You might be able to optimize over that, but I don't have time to talk about that. Okay, on the other hand, we want to prove cuts are actually all gauges. So one way to prove that is you can consider the family of depolarizing gauges that you just see in a moment. For example, a depolarizing transformation on the second qubit. We can show that this type of depolarizing gauge that is depolarizing on some subsystem actually forms a basis for all the cut space. For example, the gauge transformation I just showed here, with some calculation, you can show that the vector actually proportional to the cut vector as I draw in the graph. So as a conclusion, any vector from the cut space is actually a gauge. And as a corollary, you can see that in this kind of complete Pauli noise model, there's always 2 to the n minus 1 gauge degree of freedom. And all those subsystem depolarizing gauge give a nice basis for this cut space. Okay, so these are all about complete noise model, but as we know, if we want to make things efficient, we need to go to reduced noise model. So let's first define reduced noise model. We define a reduced model with two components. The first is XR. I call the reduced parameter space. And that means we have a reduced set of parameter, I will denote it by R, that lives in this linear space. And I also need a map Q called the embedding map that describes how your reduced model embed to a complete noise model. For example, here in the right-hand side, we have a quasi-local noise model, and this parameter, it has a few parameters characterized by R, and the Q function basically tell you how this noise model define a Pauli channel. You can similarly define a experiment on this model and learnable function on this reduced parameter and gauge transformation on this reduced parameter. And the problem here is how do we characterize the reduced learnable space and reduced gauge space, denoted by LR and TR. Okay, actually with all this very complicated linear algebra definition, the result will actually become very easy to derive. So it is shown on the left-hand side. Basically, the reduced learnable space is just a projection of the embedding map transpose of the original learnable space. And the reduced gauge space is just something like a pre-image of the gauge space via the embedding map. Or more intuitively, you can think of it, the allowed gauge embedded in the complete model is just the original gauge space take an intersect with the embedding map. Anyway, this might not be immediately clear, but one thing is definitely sure is that using standard linear algebraic method, you can first find the basis for the cycle space and cut space, and using standard linear algebra procedure to compute the LR and TR, the reduced learnable and gauge space, which should have polynomial size. But obviously, there is a caveat. The pattern transfer graph itself is exponential size. So the algorithm, of finding a basis for learnable and for the LR and TR is actually not that efficient. We don't know how to solve this problem in general, but we can analyze in this space in some specific example. So in the last maybe 2 minutes, I will just go to 2 case studies we studied in this paper. The first is we consider the fully local noise model, such that the spam noise is a single qubit polychannel, and the gate noise is only spanned on the gate support. What we're able to prove is that in this case, the only allowed gauge transformation are those single qubit depolarizing gauge transformation. This can be generalized to when you only have local spam or local gate. But I mean, the result can be slightly different, but we discuss how to analyze it. Similarly, if you have a quasi-local noise model, well, basically, a quasi-local polynoise model means a quasi-local polynoise channel is a polychannel that can be composite of polychannels supported on some subset of the qubit system. And a polynoise model is basically, if it is omega local, that means all the stipulation and the measurement and gate are also omega local polynoise channel. And we show that if in this case, if your model satisfies some covariant condition, then actually the subsystem depolarizing gauge still characterize all the allowed gauge degree of freedom of your system. What do I mean by covariant? This is a little bit annoying, but that basically means that if you assume there's a noise decomposition of your polynoise before the gate, and you commute it through the Clifford gate, it is still satisfied the same locality constraint. If this is satisfied, then I will call it a covariant noise model. But in many cases, people use is actually not covariant. Like in this example, it is not covariant. But for those cases, I just want to show that we have some case-by-case analysis. One example I don't have time to talk about, but I just want to tell you is that so in one of this paper by IBM Quantum doing error mitigation, they consider a gauge set, and in our work, we're actually able to analyze all the gauge degree of freedom in their model. Actually, there's all the single qubit depolarizing gauge that is allowed. And using that, we can be able to do some gauge-consistent error mitigation method, which is ongoing work. And maybe I can talk about that if there's questions. For the interest of time, I'll skip the error mitigation part and just jump to the summary. So in our work, we develop a framework of efficient, self-consistent gauge-set polynoise learning. We do that by characterizing learnable and gauge space using some graph linear space. And we do some case study for local and quasi-local noise model. Some outlook generalization beyond poly noise model to include mid-circuit measurement and using that in error mitigation and to have an optimal experimental design. With this, I would like to thank you and thank my collaborators. And thank you again.
So we actually don't have time for question. Please take your question offline with the speaker. Thank you.